Welcome to AI Paper Slop. Today we are looking at equilibrium reasoners. Learning Attractors Enable Scalable Reasoning by Ben-Hao Huang, Zheng Yinggang, and Zico Coulter out of CMU.
Oh, this one is huge.
Right. If you are building iterative reasoning models, you need to listen up because this paper completely redefines test time compute. And I'm just going to give you the core insights straight away to start us off.
Let's hear it.
So scaling test time compute actually works in iterative models because they learn task-conditioned attractors in their latent space. By repeatedly updating a latent state, inference essentially becomes this adaptive search.
Yeah, exactly.
And the stable fixed points in that space literally correspond to correct solutions. So by scaling depth, meaning more iterations, and breadth, meaning stochastic restarts, these equilibrium reasoners, or EQR, achieve the equivalent of unrolling over 40,000 layers.
Which is just insane to think about.
It really is. They took accuracy on the Sudoku-Extreme benchmark from a dismal 2.6% for standard feed-forward models all the way up to 99.8%.
It is a phenomenal jump. I mean, it directly answers a massive problem the community has been stuck on for a while now.
Yeah, because we all know scaling compute during inference is the current frontier, right?
Right. You see it in search-based agents and chain of thought prompting. But if you have actually tried this yourself, you know that simply looping a model's forward pass to give it more time to think doesn't automatically guarantee better answer.
Usually you just watch its performance completely collapse.
Yeah, or just plateaus. It just gets stuck. So this paper finally gives us the specific internal mechanisms for why generalizable reasoning happens at test time, rather than a model just, regurgitating memorized patterns.
Okay, let's unpack this. Let's start with the wall we've hit with standard architectures, because the baselines in this paper are super revealing.
They really are.
If you take a standard 64-layer feed-forward model, it gets exactly 2.6% on Sudoku-Extreme. It just flat-out fails.
Yeah, completely bombs it.
And if you try to brute force the problem and train a 256-layer model, your GPU just hands you an out-of-memory error.
Right, the compute scaling is just broken at that point.
Exactly. But weight-tied iterative models actually solve it.
Yeah, and to understand why, we have to look at how a weight-tied model processes information, because it's fundamentally different.
Right.
Instead of passing data sequentially from layer 1 to layer 2 to layer 3, the model takes its current thought and it loops it back into the exact same layer along with the original puzzle.
Oh, so it just keeps updating its own thought.
Exactly. It updates its thought in a recursive loop.
Mm-hmm.
You are basically taking a parameterized update operator and applying it over and over to a latent state. And that forms a learned dynamical system.
So it's basically a physics engine. It's like you drop a ball onto a mountainous landscape and you let gravity pull it down until it settles into a valley.
Yes, that is a perfect way to visualize it.
That valley is the basin of attraction. But I have to push back on the core premise here for a second.
Sure, go ahead.
If we are looping the exact same weights over and over, why doesn't the model just get stuck in a loop of its own mistakes? Like, if the weights produce a slight error on step 1, wouldn't that error compound exponentially by step 50?
That is the exact paradox the CMU team targeted.
Oh, okay. So how do they get around it?
The reason it doesn't spiral into compounding errors is because of how the training process shapes that internal landscape. The model doesn't just learn a function, it learns to literally carve out geometric valleys in its own latent space. Those are the attractors.
Wait, really? It actually shapes the geometry of the space?
Yes, and the breakthrough happens when the model successfully aligns its internal landscape with the external task.
Meaning the correct answer to the Sudoku puzzle has to physically match the lowest point of the valley in the model's brain.
Correct. The external task has a low error basin, which is the actual correct solution you want.
Right.
If the internal attractors map perfectly to that external low error basin, then the simple act of iterating the model naturally drives the state toward the correct solution.
So just finding the stable, fixed point in the latent space implicitly solves the task in the real world. That is wild.
If we connect this to the bigger picture, though, not all landscapes are going to be helpful.
Well, yeah, I mean, a model could easily learn a dynamical system that is totally dysfunctional, right?
And they often do. The authors actually map out 4 qualitative modes of these landscapes based on 2 factors, task alignment and reachability.
Okay, break those down for us.
So task alignment asks if the lowest point of the valley actually decodes to the correct answer. Reachability asks if the model can actually find that valley from its starting position.
Got it. So what does a complete failure look like mode 1?
Mode 1 is total task misalignment. There's no correct attractor at all.
Whew.
Yeah, the landscape just doesn't have a valley that corresponds to the right answer, so no amount of rolling the ball around is going to help you.
Right, it's just wandering aimlessly. What's next?
Mode 2 is a bit more deceptive. It is a landscape filled with spurious attractors.
Wait, so the model finds a stable answer, it settles into a valley, it is completely confident it is finished thinking, but the answer is just dead wrong.
That is exactly what happens. It is the geometric equivalent of an LLM confidently hallucinating and just refusing to back down.
Wow. Okay, so it rolls into a deep valley, but it's the wrong valley entirely.
Precisely. Then we have mode 3, which introduces a totally different problem, the narrow correct basin.
Meaning the right answer is there, but it's hidden.
Sort of. The right answer does exist as a stable attractor, but the valley is incredibly narrow. It is like trying to drop a marble into a shot glass from a moving car.
Oh, man. So the trajectory almost never falls into it.
Exactly. Which leaves us with mode 4, the broad, mostly unique correct attractor.
And that's the holy grail. It is well aligned, meaning it decodes to the right answer, and highly reachable, meaning the valley is wide enough to catch the ball from almost anywhere.
You've got it. And this directly explains why so many prior attempts at iterative models failed to scale. Test time scaling only works if your internal landscape is sitting in mode 4.
Because if you are stuck in mode 1 or mode 2, giving the model more iterations or more depth does absolutely nothing.
In fact, it actively hurts performance.
Wait, it makes it worse.
Yeah, it drives the model deeper into a spurious hallucinated attractor. The state settling down and stopping its changes does not equal error reduction unless you can guarantee that alignment first.
Okay, but identifying mode 4 doesn't magically build it. Like if we just try to loop a standard model to find that perfect basin, our hardware literally runs out of memory.
Oh, absolutely.
So the team had to invent a whole construction path to train this without crashing the GPUs. Well, let's look at the ingredients. They start with weight tying, obviously, to get that iterative loop.
Right.
But the second ingredient is gradient truncation with detached carry. Because if you are an ML engineer, you know that backpropagation through time is just a massive memory killer.
It's brutal. You have to save the activations for every single step of the loop. If you unroll a model for 50 steps, you are essentially trying to store 50 layers worth of activations in your GPU's memory just to calculate the gradients at the very end.
Which is why the GPUs melt down.
Yeah, so to stop that, you have to cut the backward graph into smaller segments. You truncate the gradient and detach the carry state before moving to the next segment.
But there is a massive penalty for doing that, right? If you cut the graph, doesn't the optimizer basically go blind?
It does. It absolutely does. If you use standard terminal loss training, where you only calculate the loss at the very end of the final segment, and you are using detached carry, the intermediate steps get zero direct supervision.
Oh, I see. So the model only knows if the final output on step 50 was right or wrong.
Exactly. The specific path it took to get there is completely hidden from the optimizer because the gradients can't flow backward across those segment boundaries.
You are asking the model to build a perfect landscape, but you are only grading it on where the ball ended up, not how it rolled there.
Which brings us to the real secret sauce of the paper.
Yes. Segmented online training, or SOT.
Yeah, SOT completely rethinks the optimization schedule to solve that blindness we just talked about. Instead of waiting for the final destination, SOT alternates latent state updates with parameter updates.
Okay, let me make sure I've got the nuts and bolts of this right. So instead of unrolling the model for, say, a massive 16-step rollout, looking at the final answer and trying to update everything at once.
Right, which doesn't work.
SOT takes a single step in the latent space and then immediately updates the network parameters to reshape the landscape right there underneath the model.
That is exactly how it works. It anchors the supervision along the entire trajectory.
That's incredible.
Yeah, think about it. If the model starts drifting toward a spurious attractor in step 4, like one of those hallucinations, SOT updates the parameters to correct that specific local geometry before it even moves to step 5.
Wow, so it ensures the model's intermediate states are actually viable and actively navigating toward a favorable attractor.
Rather than just wandering around hoping they stumble into the right neighborhood by the end of the unroll. Yeah.
Okay, so that solves the memory issue and keeps the model on track. Here's where it gets really interesting, though.
Oh, I know where you're going with this.
The paper introduces 2 more training interventions to explicitly force the model to carve out those massive, wide-sloping mode 4 valleys.
Yeah, they had to force the geometry to be right.
And the first one is Randomized State Initialization, or RI. And honestly, This sounds like a terrible idea at first glance.
It really does.
Like, they use Gaussian noise to radically broaden where the model's initial rollouts start. You are taking the starting point of the model's reasoning process and just scrambling it with random static.
It sounds incredibly counterintuitive. I completely agree.
Right. If I want the model to solve a highly rigid logical Sudoku puzzle, why would I start by injecting chaos into its initial thought process? Doesn't that just guarantee chaotic outputs?
I was super skeptical too, but it actually enforces a very specific mathematical property called path independence.
Okay, explain that.
Think about what happens from the model's perspective during standard training. If you start from the exact same clean, deterministic state every single time, the model learns a highly memorized, incredibly narrow path to the solution.
Like it's walking a tightrope.
Yes, one slight deviation at test time and it falls right off.
Ah, so you end up with that mode 3 landscape we talked about earlier. The correct answer is technically there, but the valley is so narrow that you'll never accidentally stumble into it if your starting position is even slightly off.
You nailed it. So by blasting the starting state with Gaussian noise, we're essentially airdropping the model into completely random, chaotic coordinates in its own latent space.
And demanding find the solution from here.
Exactly. Find your way home from anywhere. So to survive the training process and minimize the loss, the model has no choice but to carve out a massive, wide-sloping valley.
It doesn't matter where the noise drops. The gravity of the correct answer has to be strong enough to pull it down. That is brilliant. It widens the net.
It's super clever. But they don't just add noise at the beginning. They also use noise injection, or NI, which they call path stochasticity.
Right. So where RI changes where you start, NI changes how you move. They inject a small noise vector directly into the iterative update at every single step of the loop.
Yeah.
Which, again, seems like total overkill to me. I mean, if we already carved out a massive valley using the randomized initialization, why do we need to keep shaking the ball while it's rolling down the hill?
Because latent space isn't like perfectly smooth glass. It is full of tiny potholes.
Oh, like those shallow, spurious attractors.
Exactly. Even if the overall slope of the valley points toward the correct answer, a trajectory iterating its way down might get temporarily trapped in one of those potholes.
So it gets stuck in a local minimum that looks like a solution but isn't?
Right. But by injecting a tiny bit of noise at every step, you provide just enough physical jostle to knock the state out of the pothole.
Allowing it to continue rolling all the way down to the true bottom of the basin.
You've got it.
Okay, so RI widens the top of the valley to catch everything, and NI greases the slope so nothing gets stuck on the way down. I love that.
It's a very elegant setup.
But now that we have engineered this perfectly shaped landscape, how do we actually exploit it at test time? The authors introduce two-axis scaling, built around an NFE budget.
Right, number of function evaluations.
Exactly. And the NFE is calculated as D, which stands for depth, or the number of iterations multiplied by B, which is breadth, or the number of stochastic restarts.
And the interaction between depth and breadth is where things get really fascinating.
Ah.
The paper actually includes Pareto heat maps that plot out the efficiency of the scaling, and there is a very clear threshold.
Right, I saw that. Breadth scaling, meaning running multiple parallel restarts to find the best answer, is completely useless until you hit a minimum depth.
Completely useless. In their architecture, that depth threshold is around 4 iterations, which translates to unrolling 168 layers.
So let's think about why that is, using our landscape analogy. It's like dropping a bunch of explorers into a massive mountain range, right?
Yeah, that works.
If you only give them enough supplies to take 2 steps, meaning low depth, having 100 explorers out there, high breadth doesn't help you at all. None of them are going to reach the valley in just 2 steps.
Exactly. You have to give them enough steps, enough depth to actually find the basin first.
Right. Only after you guarantee they can walk far enough. Does dropping more explorers into the map increase your chances of finding the absolute lowest point?
That is a solid way to visualize it for inference. But, it leads us to perhaps the most elegant mathematical finding in the entire paper, the fixed point residual.
Oh, yes. This is what replaces the need for an external verifier, right?
It is.
Because normally if you generate 100 different answers using breadth scaling, you need a separate reward model to look at them and pick the best one.
Yes, and we all know reward models are notoriously unreliable at scale. But here, the model basically verifies itself.
How does it do that?
The residual is just the difference between the thought it had a second ago and the thought it has now. Mathematically, it is the distance between the current latent state and the next latent state after applying the update function.
Oh, okay. So when that difference approaches zero, the state has stopped changing.
It has hit an attractor.
It is settled at the bottom of the valley.
Exactly. And because we used SOT, RI, and NI to engineer a landscape where the only deep valleys are the correct answers, this internal residual tightly tracks actual prediction error.
So the model's known internal convergence is a reliable mathematical signal of correctness. You don't need a separate model to check its work.
Not at all.
So what does this all mean for real-world efficiency? I mean, we have a model that is capable of unrolling 40,000 layers to find a solution, and thanks to the residual, we know exactly when it has found it.
Right.
But running 40,000 layers for every single query would bankrupt anyone paying the server costs.
Oh, absolutely. Which is why real-world deployment requires adaptive computation. You need elastic budgets.
Okay, so how do they implement that?
Well, because the equilibrium reasoner has that reliable residual signal we just talked about, the authors can attach an internal halting head to the architecture.
Oh, nice.
It monitors the residual and adaptively allocates compute based purely on the specific difficulty of the problem it's currently facing.
So if you give it a relatively simple Sudoku puzzle, the model's trajectory might hit the favorable attractor in just 2 or 3 iteration steps.
Yeah, it finds the answer super fast.
The residual drops to 0, the halting head triggers, and the model stops computing. It uses almost no power.
But if you give it an extreme edge case, a puzzle that requires massive look-ahead and complex logic, the halting head keeps the loop open.
It just lets it cook.
Yeah. It allows the model to run for thousands of iterations, thoroughly exploring the latent space until it finally settles into the correct basin.
And when you allow that elastic 2-axis scaling to operate on a perfectly shaped latent landscape, the results are just incredible. I got to share the final benchmark numbers because they are wild. So if you take a standard iterative model without these interventions, it maxes out at 84.8% on Sudoku-Extreme and 44.9% on the Maze-Unique benchmark.
Which isn't terrible, but it shows a clear ceiling on what standard weight tying can achieve on its own.
Exactly. But when you apply the EQR interventions, the segmented online training to fix the gradients, the randomized initialization to widen the basins, the noise injection to smooth the potholes, and then you let the model scale its depth and breadth.
Here it comes.
Sudoku jumps from 84.8% to 99.8%. It essentially solves the entire benchmark.
It's amazing.
And Maze jumps from 44.9% to 93.0%.
I mean, it just proves that the pure capacity for complex reasoning was always present in the weight-tied architecture. The parameters were absolutely capable of it.
It just required the right internal physics to unlock that capacity.
Precisely.
So to recap our deep dive today, scaling test time compute is not just throwing a loop around your forward pass and hoping the model thinks harder. It is fundamentally an engineering problem.
It is.
You are building an internal physics engine where the correct answers act as gravitational pulls. You have to shape those attractors, make them broad, make them smooth, and then teach the model to reliably fall into them.
Beautifully summarized. And I want to leave you with a thought to ponder as you look at the wider landscape of AI research.
Okay, lay it on us.
Right now, almost all of our focus in scaling reasoning is heavily text-dependent. We spend massive amounts of compute forcing large language models to output step-by-step text tokens to think out loud.
Right, the chain of thought approach.
But if scalable complex reasoning is ultimately just a mathematical trajectory settling into a stable geometric basin in a latent space, what does that mean for how we build the next generation of LLMs?
Oh, wow.
Are we approaching the problem backward? Instead of forcing models to generate human-readable text tokens as a proxy for reasoning, should we be entirely focused on directly engineering the physics of their hidden states?
That is a massive question, and honestly, one that is probably going to define the next generation of architectures. We'll have to see where it goes. Thank you for joining us for this deep dive into AI paper slop. We will catch you next time.